complex numbers. These are numbers x plus iy this way, where, as you know, I is square root of -1, which is something we just have to accept, that there is this thing, the square root of -1. It doesn't exist in the real world, but let's just define I to be this thing, and let's just go forward with it. That's what complex numbers are. Okay, so we have a real part, which is the x, and then I times y, which is the imaginary part. Yeah, and we're going to write z, which is like this. And what is cool about this collection of numbers is that it actually forms a field, that we have these two operations that act in a very natural way. So addition is kind of straightforward, that if we have z1, which is x1 plus i1, z2, then we can just add them. So we have z1 plus z2 Yep, that's pretty easy, right? That's kind of natural. We also have a multiplication. So if we multiply these numbers, let me turn up the light on the board a little bit. There's, if we multiply these numbers, then we have x1. Then we just multiply through all this stuff and see what we get. So if we multiply the x1 through all this, we have x1, x2 plus I, x1, y2. And then we multiply the I, y1 through the rest of this stuff. We have I, y1, x2. And then using the fact that I squared is -1, we have minus y1, y2. And then this thing is what? Is x1, x2 minus y1, y2 plus I of y1, x2 plus y2, x1, like this. And this is our multiplication operator. This multiplies two complex numbers, gives us a complex number out. Yeah? Cool. So, what are the good things about this? Well, this is commutative. So both operations are commutative. And that's you can just check this, just do this, the Z2 in front of the Z1 comes out exactly the same way, and this is kind of obvious that it's commutative. So we have Z2, Z1, Z1, Z2, and okay. And all of you people at this point now know that there are natural mathematical objects that are not commutative. Can you give me an example of one? Give me an example of a class of mathematical.
Matrices, n-bar matrices?
Yeah. So matrices, for example, are not commutative. If we compose them, then the order at which we do it definitely matters, right? So this is something you don't have for free for every mathematical object you create, but it is true in this case. And it has the other nice algebraic properties we want. It's associative, it's distributive. It behaves algebraically just as nicely as the natural numbers, as the real numbers. And everything we want to do algebraically in terms of this kind of stuff, multiplying through a bracket, all that stuff goes perfectly well. All that stuff is perfectly good. Okay, so this is a nice collection of numbers from the perspective of algebraic operations. Everything is happening the way we want. But this is a two-dimensional set of numbers. Let me say this better. This set of numbers forms a two-dimensional object, right? Because it is defined by an x and a y. So the real numbers is obviously a one-dimensional thing. This is a two-dimensional thing. So we have this two-dimensional set that actually forms a field. It forms a field, a really nice, convenient kind of algebraically convenient way. And being two-dimensional, we like to think of this like to represent it. And we represent it as points in the plane, typically. So we're going to think of this axis as being the real numbers and this axis as being the imaginary numbers. So let me actually write that like I times R. And then everything can be considered as a point in this complex plane, yeah? Just like when we consider vectors x, y. So this is how far we are along on the x, and this is how far we are along on the y up here, yeah? Cool, so let me get rid of this because it looks ugly. So this is how we think about complex numbers, and if we think about complex numbers this way, then the additive laws just behave exactly as you would expect. So if we have some complex number x1 plus I y1, and then some other complex number x2 plus I y2, and we add them together, that's the same as taking this complex number and sticking it onto the end of this guy like this. Oops, I guess that's too long. Okay, and this thing here, see if I can change color again. I guess not. This thing here, which goes from here to here, is this vector x1 plus x2 plus I of y1 plus y2, like this. Okay, just as you learn when you were learning multivariable calculus and you were learning to add vectors, exactly the same thing happens. Oh, cool. So we can visually represent adding these complex numbers in a natural way. Yeah? Good. All right. So this is an operation we do on the complex numbers where we do the following. So if we have z, which is x plus iy, then the complex conjugate z bar is x minus iy, and of course it comes with the picture. So if this is our z, which is x plus iy, then the complex conjugate is the mirror image over here. And this is just an algebraic operation we're doing on complex numbers. It has a number of convenience properties that we will use lots of times. So this is nothing deep. It's just this thing that is notationally convenient to write that we're going to go from the complex number to the mirror image across the real axis via this operation. And here's some of the nice properties. So this is easy to see. If we have z1 and z2 belonging to the complex numbers, then just z1 plus z2. When you do the complex conjugate, just from this definition, it's kind of immediate that this is true. Okay, another thing which is true, and it's kind of another algebraic thing which is pretty straightforward, is if we take these two complex numbers and multiply them together, that's the same as the complex conjugate of each one multiplied. Okay, so complex conjugate behaves nicely with respect to this operation. That stuff is cool. All right, another cool thing. If we take z and we multiply with this complex conjugate, so we're going to take z to be x plus iy. Let's see what happened. We have x plus iy, x minus iy. When we multiply this stuff through, the i's will just cancel out each other because we're going to have an iy times x and a minus iy times x. So we're just going to have the x squared, and then this thing will be minus I squared y squared, which would just be y squared itself, which is just the absolute value of z squared. Okay, so we can quickly come up with the absolute value of a complex number by multiplying it by its complex conjugate. That's another useful algebraic fact we will use. Here's some definition. We say that the real part of this complex number z, which again is x plus iy, this thing is just the x. And the imaginary part of z, this thing is just the y. Okay, and another easy algebraic fact is that if we add together z and its complex conjugate, if we add this to this, we see that the iy thing will cancel, right? We have iy plus minus iy, right? So if we add this together, we're just going to get 2x. Yep. So if we just divide by 2, we get x, which is the real part of the complex number. Yep. And then we can do something similar to find the imaginary part. If we take z and then we minus z complex conjugate, so look at this. If we take z minus this thing, then the x's will cancel. So we'll have iy minus minus iy, which will be 2iy. Yeah? If we divide this stuff by 2i, we're just going to get y, which is the imaginary part of z. Yeah? Cool. All right, so these are useful things. Now, let's go on to the polar representation of complex numbers. So, if we have some number z, which is equal to x plus iy, recall we can think of this as a point in the plane, the complex plane, x plus iy. Polar representation of complex numbers is that we are going to represent this thing, which consists of two numbers, with a radius and an angle. And the radius is the length of the line joining 0, 0 to this complex number, and the angle is the angle from the positive real numbers. Okay? Yeah? So you learned this hopefully already, that for every xy, we can represent it with an r theta like this. Yeah? And what we are going to do here is a kind of equivalent thing. I'm going to start with defining this thing. So define e to the I theta by cosine of theta plus I sine of theta. We can define this, right? This is a well-defined thing. What is this? Well, this is effectively a map from theta to the unit circle in the complex numbers, right? So theta goes to, let me write it like this. We have the real numbers goes into the complex numbers via theta goes to e to the I theta. And what does it do? It sends theta to all things that are unit distance away from the origin. Yeah? Because as we run around theta, all of these things are complex numbers of length 1. Yeah? Everybody clear? Cool. So this is e to the I theta, okay? And the polar representation is where we write z is equal to r e to the I theta, where r is the absolute value of z, and theta is the angle that produces this thing, which is defined up to 2 pi k, where k is any integer. Right? This number, as I've written it, is not uniquely defined, because for whatever angle I have whatever pi plus this angle, 4 pi, whatever angle I have 2 pi plus this angle, 4 pi plus this angle, 6 pi minus 8 pi, whatever. It's always going to define the same angle. Yeah? Yeah? Because when we put in that into this, it's not going to change anything. If I put in pi sorry, if I put in theta or theta plus 8 pi, this produces exactly the same thing. Yeah? So this thing here, this angle is not defined uniquely, it's defined modulo 2 pi times the integers. Yeah? So we write this. So z is 2 pi like this, which is when you quotient out the 2 pi z. So i.e. we consider theta 1 and theta 2 inside this thing 2 pi z equal to each other. And this is a sentence, if this and in this group, this is equivalent to saying that theta 1 minus theta 2 is 2 pi times k for some k inside the integers. Yeah? So in this sense, it's uniquely defined, but if we just consider it on the real line, it's not uniquely defined. Yeah? And this will be actually a kind of issue we come up with. This will be important going forward. Okay, so what is cool about the polar representation of complex numbers? Okay, so what is cool about this polar representation is that it allows us to understand multiplication in a geometric way. So if we have z1, and let's write it in its polar form. So we're going to have r1 e to the I theta 1, okay? And we have z2, which is r2 e to the I theta 2, yeah? Then let's see what happens when we multiply it. So if we multiply z1 and z2, then that's going to be the same as r1 times r2 of e to the I theta 1 e to the I theta 2, yeah? Because it's commutative, I can just pull out the r1 and r2 because they themselves are just complex numbers. So I can write it this way. Everybody cool? Yeah? And then what? Then this thing is r1, r2. Let's write it out. Cosine of theta 1 plus I theta 2. Cosine of theta 2 plus I sine of theta 2. And then when we multiply that stuff out, we have r1, r2, and we're going to have cosine of theta 1, cosine of theta 2 from here to here, and then minus sine of, this should be 1 here, theta 1, sine of theta 2, just multiplying out this thing times this thing and this thing times this thing, and then r1, r2, and then the imaginary parts, which is this thing times this thing and this thing times this thing. So let's actually just put the I out here, and we're going to have sine of theta 1, cosine of theta 2, and then this thing, so we have this thing times this thing, and then this thing times this thing. So we have cosine of theta 1, sine of theta 2. Yeah, and we all recall our trig identity. So recall, having a pen here, so recall that if we have cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2, this is nothing other than cosine of theta 1 plus theta 2. It's one of our standard trig identities, huh? Identities. And we also have the following thing here. Sine of theta 1. Cosine of theta 2 plus cosine of theta 1, sine of theta 2. This is sine of theta 1 plus theta 2, another basic trig identity. Okay, so with these two facts, putting them directly into this, let's change it back to different color. So Z1 times Z2 is equal to R1, R2 of cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2, like this. Yeah. And then that thing is just equal to R1, R2 using this e to the I notation of theta 1 plus theta 2. Yeah? That's what we see just from the fact we have these trig identities and the multiplication laws for complex numbers. Yeah? Cool. So let's see what that means geometrically. That means that if we have these complex numbers, this one, Z1, so this here is the angle theta 1, and another one, let's say this guy here is Z2, and this is the angle theta 2, then what happens? Well, when we multiply them together, the thing that we get has got angle theta 1 plus theta 2 away from the positive real numbers, right? So the multiplication of these two produces this thing, which is kind of like this. This thing is got the angle theta 1 plus theta 2. Yeah? And what happens to the actual modulus? The modulus is the multiplication of the modulus of these two complex numbers. So when I say modulus, I mean absolute value. I'm going to use these words interchangeably. Okay? So the absolute value of our new complex number is the product of the lengths of the previous ones. Right? So this thing here is Z1 times Z2. Cool. So now that gives us a way to understand geometrically both of the field operations of the complex numbers. When we add the complex numbers, we are just adding the vectors in the way that we've learned to add vectors. That thing is quite standard. Now, this multiplication operation, we understand what that thing is doing. It's taking our two complex numbers with our angles, yeah? And when we multiply them, the new complex number is the sum of these two angles times the multiple of the length of the absolute value, times the product of the length of the absolute values. Yeah? Which is a very neat geometrical thing to understand. This is a very clear thing. So previously this algebraic operation of multiplying, which was consistent with the fact that we have defined -1, or we defined I to be square root of -1, this now has meaning in terms of seeing what these complex numbers do to each other when we multiply them together. Yeah? Cool. And that's going to be very useful for us going forward, as we'll see. Another thing to note is that if you don't remember your trig identities, which I certainly don't, you can always recover them from this fact right here, right? So if you remember the fact that when you multiply, so just note, if you remember your complex analysis, that when you multiply this complex number with this complex number, it's equal to this complex number. We use the trig identities to get this fact, but if you assume this fact, you can get back the trig identities, right? Because if you write out what this means that this thing here, which is this thing here, this thing, which is this thing, is equal to this thing, which is this thing plus I times this thing. Huh? So from this, you can recover these two trig identities. Yeah? So you don't have to struggle with remembering these things. This is quite an easy thing to remember. And this thing implies both of these things just by writing out the real and imaginary parts of this complex number and this complex number. Yeah? So, and actually, okay, let me not go into a tangent. So this thing is a cool thing to have in mind when you want to recover trig identities.